Okay, so now we're going to talk about regression. Given a collection of paired sample data, the regression equation y hat equals b naught plus b1x, so that's y hat. Um, this is the algebraic description of the relationship between the variables x and y. And when you graph this regression equation, you get the regression line. Now, the regression equation can be used for prediction. You can use the regression equation to predict values of y given values of x or vice versa. But what you want to do is you want to make sure that the regression equation is actually a good model. So here are the questions that you ask yourself, or here are the things you have to do to determine whether the regression equation is a good model. First off, the regression line graphed in the scatter plot shows that the line fits the points well. If you graph the regression line on a scatter plot, there should be some um, indication that the line fits into the points well. The second thing is R indicates that there is a linear correlation. So basically, that's the most important one. You have to make sure that there is actually a linear correlation and use the linear correlation coefficient R for that. The third one, um, the prediction is not much beyond the scope of the available sample data. So that means if you have um, first coordinates in your ordered pairs that range from let's say 5 to 17. So this would be the minimum x value, and this would be the maximum x value. So if this is your minimum and maximum x value from the ordered pairs that you use to create the regression equation, you're not going to try to predict the y value when x is, let's say, 38, because that would be well outside of the range of what your sample data had available. I mean, that's well outside of the scope of your sample data. So as long as you stay very close to this range, you should be okay. But going far outside of that scope would be a violation of this one here. So those are the three things that you have to look at to make sure that you actually have a good model, that y hat is actually a good predictor for y. And if you answer all these and you get that, yes, this is a good model, you answer that question yes, then you can use the regression equation. You just plug in the x value and get the y value, y hat. Now, if your answer to these is no, like for instance, the main one would be that the R indicates that there is no linear correlation. So that's the main one we'd look at. If that one is saying that there's no linear correlation, you answer this no, and you would just use the value of y bar. You use the average y value to be the best predicted value. So instead of using y hat, you'd use y bar. So y hat is the value that comes from the regression equation. Y bar is the mean value of all the y's. So you add up all the y's and divide by n. Okay, let's look at these examples here. Okay, making predictions. In exercise 5 through 8, use the given data to find the best predicted value of the response variable. Be sure to follow the prediction procedure summarized in figure 10-5. That's the prediction procedure we just went through in 10.5. So, let's look at number 5. Number 5 says, in a study conducted by the University of Arizona researchers, the total weight in pounds of garbage discarded in 1 week and the household size were recorded for 62 households. The linear correlation coefficient is R equals 0.759. The regression equation is y hat equals 0.445 plus 0.119x. So 0.445 is the y-intercept and 119 is the slope, where X represents the total weight of discarded garbage. So X is the total weight of the amount of garbage that they threw away in 1 week. And the mean of the 62 garbage weights was 27.4 pounds. So that would be X bar. 27.4 pounds would be X bar. And the 62 households have a mean size of 3.71 people. So that would be Y bar. That would be the size of the household. What is the best predicted number of people in a household that discards 50 pounds of garbage? So now we're giving us an X value and they're asking us to predict a Y value. So they're asking for Y hat if X is equal to 50. Actually, we don't know if we should use Y hat or if we should use Y bar. Y bar is 3.71. So Y bar is the mean household size, which is 3.71. So we don't know if we should be using, if we should plug the value 50 in and find the value of Y hat, or whether we should use Y bar. Well, let's see. In order to determine that, we have to go through these three bullets. And we're just going to check this one. R indicates that there is a linear correlation. So let's see here. R indicates that there is a linear correlation. So our value of R is 0.759, and our value for N is 62. On the chart, we don't have 62, so we're going to round it to 60, and we're going to look at the row that has N of 60, and we're going to take that value, and we're going to take those values, and we're going to compare it to R. Well, the value we have for R is bigger than both of these numbers for a 5% significance level and for a 1% significance level. Our value of R is greater than both of those. So in that case, we reject the null hypothesis. The null hypothesis is that rho is equal to 0 or there is no correlation. So since we're rejecting that, we're saying that there most likely is a correlation. Rho is not equal to 0. So there is a correlation between the amount of garbage you dispose of in 1 week and the size of your house. And in order to calculate the best predicted value, we're going to use Y hat, which is going to equal 0.445 plus 0.119 times X, which is 50. So let's go ahead and calculate that. So we get Y hat is equal to 6.4 people. Okay, so that is the case here where there was a linear correlation between the two variables. Now let's look at an example where there is no linear correlation. So for this one, we found a predicted household size for 50 pounds of this discarded garbage to be 6.4. Now let's take a look at number 6. In number 6 it says, a sample of 8 mother-daughter pairs of subjects was obtained. Their heights in inches were measured. The linear correlation coefficient is 0.693 and the regression equation is y hat equals 6.9 minus 0.0849x, where x represents the height of the mother. So we're using the mother's height to try to predict the height of the daughter. The mean height of the mothers is 63.1 inches, and the mean height of the daughters is 63.3 inches. So 63.1 would be x bar. That would be the average x. And 63.3 would be y bar. That would be the average y value. Okay, so find the best predicted height for the daughters. All right, well, we have here our correlation coefficient 0.693. So 0.693 is the correlation coefficient, and there are eight ordered pairs, eight pairs of mother-daughter, or eight mother-daughter pairs, and their correlation coefficient R is 0.693. So we go to the row that has eight, and let's see. Our coefficient R is 0.693, which is smaller than both of these numbers. So since R is smaller, we fail to reject the null hypothesis, which means there's no correlation. That rho is in fact equal to 0, so there's no correlation between the height of the mother and the height of the daughter. So therefore, the best predicted value for number 6 is going to be y bar, the average height of the daughters, not the value we get from plugging x into the equation, but the y bar, the average height of the daughters, which is 63.3 inches. So the answer for number 6, 63.3. We don't use y hat in that situation. Okay, now I want to take a look at number 9 here. And in number 9, we're going to use the given data to find the equation of the regression line and examine the scatter plot and identify characteristics of the data that is ignored by the regression line. Okay, so let's go ahead and pull out the TI-83 calculator. So we're going to take our 11 ordered pairs and we're going to put them into the list. So we hit stat, then we go to edit, and we put the ordered pairs into lists. We put the x values into list 1, we put the y values into list 2, so that all 11 values are in the list. Then once we have all 11 values in the list, what we're going to do is we're going to hit second and quit, and we're going to go back to stats, we're going to go over to test, we're going to go down all the way to letter E, the lin-reg t-test. Press enter, and the x list is list 1, the y list is list 2, and the alternative hypothesis is that there's no correlation. So we go to calculate, we press enter. Okay, now we have y equals ax plus b. So let's see if we can answer some of these questions. It says use the given data to find the equation of the regression line. Well, the calculator is giving me y equals ax plus b. That's what the calculator is giving me. And if I use y equals ax plus b with these values that I'm given here, I come up with an equation of a... Alright, and let's see some of the values that we're given here. Alright, so one of the values that I'm given is I'm giving t, which is 4.221. That's the test statistic. Really, what we would need is the p-value, and in this case, the p-value uh, p-value is equal to 0.002, and a is equal to 3.008, let's call it, and a is given and b is also given as 0.4997. So we get a and b. We also get a value for r. We get r to be 0.815. All right, now using these, we also get in the window that we can use y equals a plus bx. Let me show you that here. If you look in the previous window that we were in, You see, it says linreg t-test y equals a plus bx. That's the linear equation. So that's our b naught and b1 from the book. They call it something different in the TI. So from our book, b naught would be a, and b1 would be b. And in general, this would just be, well, let's not go there. M and B, which come from the slope-intercept form y equals mx plus b. But anyway, um, we get this equation for the prediction equation y hat, and this is the p-value, 0.002. We're either going to use the p-value or we're going to use R and table A6. Table A6. But in either case, we're going to reject the null hypothesis because the p-value here is smaller than any value of alpha, 0.05 or zero point zero 0.01. And when we use table A6, we're going to get the same result. So there is a linear correlation, so we are going to use y hat as the best predicted value for our data, for our y. All right, now, so the regression equation then, y hat, which is going to be the predicted value, is going to be 3.008 plus 0.4997x. So that is going to be the answer for part A. The equation of the regression line is this. And then it says examine the scatter plot and identify characteristics of the data that are ignored in the regression line. Okay, well, let's see. Let's bring back out the TI 83 calculator here. And what we're going to do is we're going to graph this. So we're going to go to stat plot, and we're going to turn plot 1 on, and we are going to do a scatter plot. The data are in list 1 and list 2. We're going to use dots again. And now we go to zoom, and we go down to zoom stat so we can see this scatter plot. Zoom stat is here. Ah, well, there is the data graphed. Interesting. So let's see. Now let's graph the regression equation. So y equals, and let's clear this one. And let's go and graph our regression equation by going to vars, and then going down to statistics, going over to EQ, and grabbing the regression equation and putting it in here. This is the regression equation. And then we go back to the graph, and there's the regression equation going through the data. Now, examine the scatter plot and identify the characteristics of the data that is ignored by the regression line. Well, the regression line says that there's a positive correlation here, and there's definitely a positive correlation, but I don't think it's a linear correlation. It kind of looks like a parabola. I think we could get a quadratic fit that would fit this better. Actually, it looks like a quadratic fit would be perfect for this one. So um, without looking at the actual scatter plot, sometimes we miss things if we just look at the equation. All right.